Last class we discussed about the force that is due to two charges, two stationary charges, and we extended that up to what is the force due to multiple charges. Now today we are discussing about electric fields. Before going into that, last class we discussed the force due to multiple charges. Let me write it once more. It is, we have 1, 2, 3 charges. So one is Q1, the other is Q2, Q3, and we have a test charge capital Q here, and we have the separation vectors, that is R1, R2 and R3. So that is R1, R2 and R3, and we found the force. How to calculate what we were discussing is that how to calculate the force due to all these three charges on the test charge, and we wrote it as F is equal to F1 plus F2, F1 plus F2 plus F3. Okay. Now what was that F1? We can write it as that is 1 by 4 pi epsilon 0. F1 is 1 by 4 pi epsilon 0 Q1 into Q divided by R1 square into R1 cap, and F2 is Q2 into Q divided by R2 square, and F3 is Q3 into Q divided by R3 square into R3 cap. Okay. That means in all that there is a 1 by 4 pi epsilon 0 is common, that is in F1, F2, F3 all over there is a 1 by 4 pi epsilon 0. So I am taking it outside. So 1 by 4 pi epsilon 0, then the remaining will be for the first force, that is Q1 into Q divided by R1 square into R1 cap, plus the second one, that is Q1 into Q2 into Q, because the second force, that is Q2 and Q2 into Q divided by R2 square into R2 cap, plus Q3 into Q divided by R3 square into R3 cap. Now let us take that Q as common outside. Now if I take that Q outside, then taking the remaining, that is without a Q, I am taking all this remaining together, that is 1 by 4 pi epsilon 0, 1 by 4 pi epsilon 0 Q1 divided by R1 square into R1 cap, plus Q2 divided by R2 square into R2 cap, plus Q3, sorry, the second one is Q2. So Q3 divided by R3 square into R3 cap. Now what we have done here is we took the capital Q, that is the test charge outside, and the remaining is put in a single bracket. Now what is this thing that is in the that curly bracket? Now here we have a bracket and here we have a curly bracket. What is that term that is inside the curly bracket? Let me call it as E, that is Q times E. We call that as E. Why that is a vector? Because there is R1 cap, R2 cap, R3 cap, that is each of these terms are a vector, so the sum will also be a vector, and we call that particular sum or that particular term as E, the electric field due to these three charges. To find what we have done here, we removed the charge. That means we know the expression for force and we removed the source test charge from there, and without a test charge what is there? That is my question. That is, if there is no test charge, imagine, that is if I remove this test charge, then what would have been there? Is there anything there? Actually there is nothing, but we can assume there is something, that is there is no thing that is a physical thing is nothing there, but we can imagine something that is this expression, this electric field was there. And how do we get the force? When the test charge, that when it interacts with the electric field, we get the expression for the force. So that is why we got an expression F is equal to QE. Actually, what we are doing here by introducing this E is, the purpose of that is actually the whole point of electrostatics is done already with the Coulomb's law and superposition principle itself. But and what is really or physically is there is only the force. Then why we are introducing this imaginary thing called the electric field? Because it makes our calculation more easy. That is every time you do not need to calculate the F directly. You can calculate the E, the electric field at that point, and whatever be the test charge. Sometimes I have to use Q is equal to some 1 coulomb. Then put that 1 coulomb here, multiply the electric field, you get the force. And if I replace that Q with the 2 coulomb, you do not need to replace it everywhere in this equation, in this force equation. You just replace it here and you can calculate the field. And when we are dealing more, or when we are go into this topic more and more, you will see that it is much easier to calculate electric field than the force. So this becomes more easy to find the force. That is why we are introducing a new quantity that is called electric field. So that electric field, or we can physically say that electric field is equal to, from the above equation, is equal to F divided by Q, that is the force acting per charge, that is the force acting per charge is called the electric field. We can physically define it like that. Okay, now we can take the expression of electric field only from this equation. So then what is the electric field? See, now we do not need this test charge, we are removing this test charge, we do not have, and now onwards we call this point. Now also we have this point because we calculated, or we calculate the electric field at this point, or this term is actually the electric field at this point, and which has a particular direction also. So we are calculating the electric field at this point, that's why we call this point as field point. So now onwards this point will be known as the field point, and this will be the source charges as discussed before. Now let's write the expression for electric field law. Okay, now the electric field E is equal to, since there are multiple charges, we write the expression as seen before. Now we are considering only this single charge, that is the Q. So if there is only a single charge, then the expression for this electric field E is equal to 1 by 4 pi epsilon 0 Q divided by R square into R cube. And here also you see that electric field is a vector quantity, and electric field has a direction which is the same direction as that of the force experienced by a positive charge. So if you want to find the direction of electric field at a particular point, you can do this. Suppose you have a charge here. Imagine you have a charge Q here, and you want to find what is the direction of electric field at this point P. Okay, what you have to do is that you take a charge, particularly a positive charge, take a positive charge and place it here, and I am placing a positive charge here, some plus Q here. Now imagine that here you have a Q, and here we have a Q, and imagine that here we have a plus Q. Then this is positive and this is positive. What would happen, or what would this Q do to this capital Q, that is on this test charge? You know that both are positive, so this small q, that is the source, will push away, that means they repel each other, or it will push away the plus q, or the force acting on this plus q will be along this direction. So this direction will be the direction of electric field also. So if you want to calculate the direction of electric field at any place, place a positive charge there, then imagine where it would move, or what is the force acting, what is the direction of the force acting on a positive charge. That is a must. You have to put a positive charge there, not a negative charge. If you place a negative charge, then the force will be towards here, but that is not the direction of electric field. To find the direction of electric field, you place a positive charge there, then find the direction of force on that, then that will be the direction of force. Now let's draw the direction of electric field around a positive charge. You have a charge, that is, let's map all the force around this charge. So you have a charge q here. Now I want to find the force, field, the direction of the field around it. So I place a charge here. Now imagine that here you have a positive charge. Then what will happen? This positive charge, this small q will repel this positive charge along this direction, because it's a repulsion. Since it is a positive charge and this is also a positive charge, the like charges repels, so this will move like this. Now what will be the force at this point? I am placing again at this point a positive charge, and this is a positive, this is a positive, and they will repel, so the direction will be along this direction. And at this point, what would be the direction? Here also I am placing a positive charge, and they will repel, and here also they will repel, and I can do it for every point. So I will get something like this, that is electric field around a positive charge, that is electric field around a single positive charge is always outwards, and you can see that is exactly the radius. That is, if you draw a circle here, you can see that they are radially outward, and you see that this is not just a circle. The electric field is not a two-dimensional thing that we draw on a board. Actually it is a three-dimensional thing. That is, suppose you have a charge here, the electric field is not only just on this plane, it is actually, it is into towards you, away from you, and everywhere. It is a spherical thing. So when I am drawing a circle like this around a charge, you have to imagine that here we are drawing a sphere towards here, and into the board also you have a sphere here, and all this electric field is passing through that imaginary sphere. So it is not a two-dimensional thing, it is a three-dimensional thing. So there is some forces that is coming towards you, electric field coming towards you, this side, into the board, and everything. So this is how the electric field of a positive charge looks like. Then what if it is a negative charge? It's very simple. The same procedure we can do. How? So you have a negative charge here, and place, now we want to calculate the electric field due to this minus q. For that, again take a positive charge. Even though the field is calculating for a negative charge, we have to put a positive charge around it to find the direction, not a negative charge. So to test the direction of the electric field, you always take the test charge as a positive charge. So I place a test charge here. Now that is a positive charge, and this is a negative and this is a positive. What would happen? They will attract. That means this negative charge will pull, pull this positive charge towards the source charge. So now the positive charge is here, this will attract towards here, towards here, towards here. So if I extend that, you will get something like this. Again I am mentioning this is not a two-dimensional thing, there is vectors that is moving towards from here, from here, from here, and as well as a three-dimensional thing, like before. So this is the direction of electric field around a charge minus q. We will discuss it later when we are dealing electric field lines. Now we know how to calculate the electric field due to some charges, and we know the expression for this as E is equal to 1 by 4 pi epsilon 0 and if you have multiple charges, then you have to find, I can write it as some summation I is equal to 1 to n. Suppose imagine that we have n charges, then first charge divided by that separation vector times square. So, that is Qi and Ri square into Ri cap. So, if you have any confusion in this summation convention, you can put each values there. Let me put each values there. So, then you will be clarified. This is the same equation that we wrote before. So, 1 by 4 pi epsilon 0, that is common. Now, you put the value 1. So, if I give the value 1, what this will be Q1 divided by R1 square into R1 cap. So, the first term. Now, this is a summation. So, plus the next index, that is I is equal to 2, that is Q2 divided by R2 square into R2 cap plus etc. up to Qn divided by Rn square into Rn cap. So, this is it. This is how the expression. Now, if we have any discrete charges that is distributed anywhere, we can calculate the electric field using this. Here also, actually, if you look into that, let us draw 3 charges Q1, Q2 and some Q3 here. Now, we are calculating the field at this point. Let that point be P, and we call this point as the field point. So, we want to find the field at this point. So, what we are actually doing is that, let us look for the first term, that is the electric field due to this Q1, that is 1 by 4 pi epsilon 0. So, that is 1 by 4 pi epsilon 0, that is common, plus this term. What is this term? Q1 by R1 square into R1 cap. Actually, this distance is R1. So, Q1 divided by R1 square into R1 cap is the electric field due to this first charge. So, or else we can write it as this is actually our E1, that is the electric field due to the first charge. And what is the second term? Let us look into that. So, this is the second term, that is Q2 and the field point, that is Q2 divided by R2 square into R2 cap, that is the E2. So, we can call it as E2, that is the force, this is E2. So, actually here is also we are applying a superposition principle of electric field. That means when you have multiple charges and you want to find the electric field at a particular point, you have to calculate the electric field due to each charges, that is E1, E2, E3 etc. and up to En, and take the vector sum. That is exactly same that we are done for the forces, but except there is no test charge here, we have only field here. So, this becomes finally the answer becomes what is E1 plus E2 plus E3 etc. up to En. So, this is the same superposition principle that follows at here also for electric field also. Actually, there is not that much difference between electric field and force except that for a test charge. So, that is why it also, the electric field also follows the superposition principle. Now, let us do a sample problem using this concept, that is how to calculate when we have multiple charges and how do we calculate the force due to all of them. So, for that, you have 2 charges. So, you have 2 charges, one is here and one is here, each of magnitude Q and Q, they have same magnitude, and from the we want to calculate the electric field due to these 2 charges. Now, we have 2 charges and we want to find the electric field at a particular point. The point is exactly above the midpoint, exactly above the midpoint of this line at a distance Z from the midpoint. Okay, so this is, so we want to find the electric field at this point P. What is the electric field? So here P, that is P is the field point, and we have two source charges, that is Q and Q, and the distance between these two charges is given as D. So the totally this is D, that means one segment will be D by 2 and this will be D by 2. Okay, this is the problem. Now how would we calculate the force due to all this? So before going into that, we can do it in several ways. Probably you have done something like this in your +2 classes, but we are doing it in a little bit complicated way, but which is very useful when we are dealing with there are multiple charges or when we are dealing complex problems. So we are going for a general approach for that. So as already I mentioned, we need a coordinate system to mention its position vectors. That is, we need a source position vector, a field position vectors, that is our old r dash and r. So let's set up a coordinate system for all this. Okay. Now let's this be the origin of the coordinate system. That means we took the midpoint as the origin, and we have a direction towards here. So let me draw it something like this. Okay, that is, let this be the positive x direction, and then this will be the negative x direction, and the upward direction, let it be some z direction. So this dotted line shows our imaginary axis, some x axis and an z axis, and obviously there is a y axis that is pointing towards you, but here we do not need that to calculate all this. So we are ignoring that y axis. Now you have the x axis and the y axis, sorry, and the z axis. You can take it as y, no problem. Then why I took it as z? Because I have given this distance as z, that is why I called it as z. There is no problem in that. Anyway, this is the z axis. Now we have two charges, but both are same, q and q, but to identify between them I am giving an index. Let this be the first charge. That doesn't mean, and this is the second charge, that doesn't mean that they are different. They have the same magnitude and same polarity. That means they are both are positive. So 1 and 2 is to identify them. So take the first charge, take the case of the first charge. So now we want to, how will we calculate the total field? We want to calculate the field at the point P. How will we calculate that? First of all, we will calculate the force due to this charge, that means the first charge, and then we will calculate the force due to the second charge, sorry, electric field due to the second charge, and we will sum it up to get the final answer. But here the problem is we have to set it up, the old r and r dash and everything. Okay, now let me go back to that. We had something called r, that is the curly r, that is the separation vector, and there is something called r dash, that is the position vector of source charge, and we have some r, that is the position vector of the test charge. Now we do not have any test charge here because we are not calculating the force, but we call this point as a field point. So here onwards we call this r as the position vector of, not the test charge, position vector of the field point. So point where we want to calculate the field point. And as we have done before, we know that the curly r, that is the separation vector, is equal to r minus r dash. Okay, now we have two separation vectors here. Let me draw them first, then we will calculate the position vectors and all. So this is the first separation vector. So separation vector is always directed from the charge or the source to the field point. Here is also another one, this is the source, this is the field point, so this is that. Okay. Now we have two separation vectors, and let me call it as R1 and R2. Also we have, this is one of the source charges, and for source charges we give a position vector. That position vector is denoted by R dash. So for the first charge we put a vector here, so that is from, let me put it in a different color. So let me take this. So okay, now so this is the vector. Actually it is along the line, along this white line itself. So this line is called the R1 dash. That means the position vector of this charge. Similarly here is also we have another position vector for the second charge. So we got two of them. Now there is one more position vector, that is the position vector of the field point, that should be directed from the origin to the field point. So I am drawing that too. So now let me label each of them. This is the source vector, source position vector of the first charge. So that is why I am giving it R1 dash. Okay, and this second vector is it is actually this R dash, but for the second one, so that is R2. Now this is only one vector, so I can call it as the field position vector of the field point. That is only one, that is a common one. So R, this will be always 1 because we have only one field point. That is, we want to calculate the field at a single point. That is why always it will have a single. There is no R1 R2 thing like that. That is why, because there is only one point. So that is R. Okay. Now all the labeling and everything is done. You may think that it is getting bit complicated. You can do the same problem very simply, but we are making it more complicated to do some difficult problems. That is why we are making, this is the actual approach we have to do with all the meaning of this separation vector and everything, and we will get the answer directly from all this. You probably you may remember that you have done this same problem in the +2 classes by taking the components and resolving and everything, but always it is that much useful. So that is why we are using something like this. So now consider the first charge. So now I am rubbing it on this. What we need is only this equation. So let me place it somewhere which is visible. So the first charge. So for the first charge, find the R1. So R1 is equal to what it would be. So R1 is equal to R minus R dash, that is R minus R dash. So that is R minus R dash, but R is R1 dash because we are dealing with the first charge. So now what is R? You see that the R vector is this one, this yellow vector, and what is the specialty? It is directed along the Z direction and it has a magnitude Z itself. So I can write that vector as Z. It is directed along the Z direction, that is why I put Z cap, that is the unit vector along the Z direction, minus R1 dash, that R1 dash is, what is that? It is directed, this is this vector, that is the R1 dash, this is directed along the negative x direction. This is the positive, this is the negative x direction, and which has a magnitude d by 2. So let me put that d by 2 here, and it is directed along the negative x axis. So I have to put a negative x cap there. So finally what it becomes, Z into Z cap plus means this minus into minus, that is plus into d by 2 x cap. Now let me write the final expression for the force. So the electric field, that is electric field due to the first charge, which is equal to 1 by 4 pi epsilon 0 into first charge, that is epsilon 0 into first charge, that is q, divided by the R1 square, that means this separation vector square. So what is the square of this vector? This is r1. What is the square of it? That is, you know that's how to take the square of a vector, that is take the square of individual components. That is, here this is the z component, so this is z square plus d by 2 the whole square, or d square by 4. Okay. Now this is the direction of that vector. Sorry, this is the square of the distance between them. Now that's okay. Now what we need is the r cap. How will we put that r cap there? So to find the r cap, you have to take, you know that how to find the unit vector. Suppose we have a vector A. To find the unit vector, what you do is that is a vector A divided by the modulus or the magnitude of A. This is the equation to find the unit vector. Let me use that. Now we want to find r1 cap, which is equal to vector r1 divided by the magnitude of r1, which is equal to, what is r1? r1 is z cap plus d by 2 x cap plus d by 2 x cap divided by the magnitude of this vector. How to find the magnitude of this vector? Take each component and square it and add it and find the root. That is, here the first component is z and the second component is d by 2. Take the square, z square and d by 2 the whole square, and take the sum, that means z square plus d by 2 the whole square, and finally take the root, that means z square plus d by 2 the whole square and whole raised to 1 by 2. And now let's substitute this back into our equation, and we get, that is 1 by 4 pi epsilon 0. Here we have r1 cap. Instead of this r1 cap, we have to substitute all this together. When it comes to this, that is q divided by, that is in the numerator we have z cap into d by 2 x cap, that is I'm just wrapping it up. Okay, now this is z cap plus d by 2 x cap divided by, this is z square plus d by 2 the whole square, the whole raised to 1 by 2 into the previously z square plus d by 2 the whole square into z square plus d by 2 the whole square, the whole raised to 1 by 2. So this together becomes, this is the whole raised to 1 here, this is whole raised to 1 by 2 here. So the answer is q, in what happened, this 1 plus 1 by 2, that is the whole raised to 3 by 2 it becomes. So in the next step it becomes, the E1 is equal to 1 by 4 pi epsilon 0 q into z cap plus d by 2 x cap divided by z square plus d by 2 the whole square, the whole raised to 3 by 2. So this is E1. Now we got the expression for the E1. What was E1? E1 was the force due to the first charge. Now we have to calculate the force due to the second charge Q. So second charge is here. Now we have to do the same set of procedures here. That is, we have to find what is R2. That is, R2 will be, I'm not exactly solving that you can do it as yourself. This is d by 2. That is, you can calculate R2. The vector R2 will be, you can see from here, this is the R2 dash. That is, this vector is the R2 dash, or R2 is equal to, we can write it as R minus R2 dash. Now what is R? R already we have seen that Z cap minus what is R2 dash? R2 dash is this vector, that is d by 2 along the plus axis, that is d by 2 x cap. Now we got R2 here. Now we will set up the equation for the second electric field, that is, so E2, which is equal to 1 by 4 pi epsilon 0 Q into, here what is we need, R2 cap. So instead of R2 cap, what will we substitute? We will substitute Z cap minus d by 2 x cap whole divided by, so we can put a bracket, okay, Z square plus d by 2 the whole square, the whole raised to 3 by 2. Now we got two vectors, two individual vectors that are the field due to the first charge and the second charge. Now take the sum, just take the sum of these two quantities, which is very easy. So the total electric field is equal to, you can see here, now this Z cap plus d by 2 x cap, and here you have a minus d by 2 x cap. When you add this together, this 2 d by 2 and this d by 2 will be cancelled. Then here is one Z cap and here is also another Z cap. They will sum it up to get 2 Z cap. So our answer will be 2Q into Z cap divided by 4 pi epsilon 0 into, let me write it some compact way, that is, yes, 1 by 4 pi epsilon 0 into, they add up to 2 into Q into Z cap divided by Z square plus d by 2 the whole square into 3 by the whole raised to 3 by 2. This is the final result. You can cancel it out, but most of the time we place it something like this, because we need later when we learn about the dipole, we need this equation. We will get back to this equation with the two opposite charges. In the previous case, we placed two equal charges here, that means same polarity. When we are dealing with the dipoles, we will come to this with the two opposite charges but with the same magnitude. So finally we got the answer, and this is how you have to calculate the electric field due to multiple charge configuration. And when we have a lot of charges there, it will be it will have a multiple number of terms. And in the next session we will deal what if the charges are continuous. That means now the charges are discrete, that is Q1 here, Q2 here, Q3 here. The next case we will take another kind of charge, that means a charge is distributed over some area. It is completely filled by charge. How will we calculate the field of that? We will discuss it about in the next class. And this is for enough, I think this is enough for this class, and winding up. Thank you.